Greetings, comrades. We're talking about JavaScript. There actually won't be a lot of JavaScript tonight. There's a whole lot of backstory that I think we need to get to before we get to JavaScript. So tonight is going to be Volume 1, The Early Years. And I'll start with some of my own history. But first we'll start with Woody Allen. In 1969, while I was in high school, Woody Allen made a movie called Take the Money and Run. In the movie, he plays Virgil Starkwell. And in this scene, he's interviewing with an accounting company for a job, something for which he is completely unqualified. The interviewer asks him, do you have any experience running high-speed automatic digital computers? And Virgil answers, yes, my aunt has one. He says, what does your aunt do? He says, I can't recall. So it's funny because, you know, that a completely nerdy young man would have less experience with computers than his aunt. It's just ridiculous. Except when the movie came out, it was funny for a completely different reason. The reason it was funny in 1969 was that computers were incredibly expensive at that time. They cost millions of dollars. They required a room as big as a house, literally with a raised floor and special air conditioning and fire suppression systems. They required a lot of people to operate them and to manage them and to perform maintenance on them. They took a lot of power to operate. It's sort of like the expense of running a colo for one CPU. And so computers would be available only to very large corporations, large government agencies, very well-endowed universities, and nobody else. It was completely impossible that anybody's aunt would have one. So in order to understand this story, in order to understand why it's funny, you need to understand the context behind it, and that's what we're going to be doing tonight. As far as my own story, I wanted to have a computer. But they were just not available. I only knew two people who actually had them. One of them was Napoleon Solo, the man from U.N.C.L.E. He was able to have one because he worked for the United Network Command for Law and Enforcement, and they had a lot of money, and so he had a really nice-looking computer there. The other person was Batman. He had his Bat computer, and that was because he had access to the wealth of millionaire Bruce Wayne. I didn't have resources like that, so I decided I was going to build my own. And at that time, I had absolutely no idea what computers were or what they did or why I wanted it. I just knew that I wanted it. And I couldn't even identify all of the components of one, except that I knew that they had consoles that had lots of lights and buttons on them. And I thought, I'll start with that. So I'll make a console, and then I'll work out the rest of it. So I found some pieces of particle board and a saw, and I sketched out what it was going to look like and started sawing. And I sawed and sawed and sawed. The particle board was really, really hard, and the saw was really, really dull. And I sawed and sawed for what must have been at least 2 minutes. And then I gave up. Said, okay, I'm not going to do that. So I probably went in the house and watched television after that. So at that time, even at that tender age, it was already obvious that I was going to be a software guy. So having established my credentials, my qualifications for giving this talk, we will now proceed. So there's a lot of history that I'm going to give you tonight. I think it's really interesting stuff. And I'm going to spend this time with you today because I think it's important that you know it too. Most of us are not aware of our own history, the history of our own field, and you need to be because there's a lot of rich material here. But there are a couple of recurring themes that I'm going to identify. The first is that people who should be the first to recognize the value of an innovation are often the last. And we're going to see lots of cases where this has occurred. Obsolete technologies fade away very slowly. We like to think that innovation causes everything to move over. It doesn't. And sometimes we step forward and sometimes we step backwards. And sometimes we step both ways at the same time. Sometimes stepping backwards is the right thing to do. Sometimes it's a bad thing to do. At the moment, we never seem to know the difference. There's also a myth of inevitability, that the reason things are the way they are is because they had to be as a consequence of everything that happened before. So the reason we have the things that we have is that's just the best way that it could have worked out. And that's absolutely not the case, and I hope to demonstrate that as well. So I'm going to be weaving some threads together. So let's start with the Jacquard loom. Joseph Pierre Charles de Jacquard perfected the loom, the automatic loom, in 1801. And this is what it looked like. He adapted player piano technology to automate the operation of a loom. So each card represents the pattern on one row of the thing that's being woven. And instead of, in the holes and spaces, instead of causing hammers to go down onto strings and back up again, instead would control the movement of threads within the loom. And he didn't do the continuous roll that the player pianos did because that was just way too difficult to edit. So instead he had them, each row as a separate unit, and he would then sew them together. So it was a much easier thing to create. It was an extremely effective device that a weaver using a Jacquard loom could outperform a master weaver and an apprentice on a draw loom by over a magnitude in efficiency. Just an amazing difference. The Jacquard loom became very successful, and these principles were applied to other forms of automation. And whenever you have a big breakthrough like that, there are always other things that get invented as a consequence. And one of the big ones was industrial sabotage, because it turned out the weavers didn't like this. He was completely upsetting the way that they used to live. So they went around and would find Jacquard looms and destroy them. That's what they did. Now, there are some people who did identify other uses for this. For example, Babbage and Lovelace recognized the potential of using punched cards for moving data in and out of their computing engines. Unfortunately, Babbage never finished his machine, so that's sort of a dead end. So the story picks up with the Hollerith card tabulating machine in 1890. The United States Constitution requires a census every 10 years, in which we go and count all of the citizens, and we use that information to determine the composition of the House of Representatives. The country had gotten so big by the late 19th century that it was becoming more and more difficult to count how many of us there are. Hollerith, Herman Hollerith, invented a machine and showed it to the Census Bureau, and they accepted his bid, and this is how the 1890 census was done. So a clerk would take a questionnaire, which you can see in his left hand, and copy it onto a punch card using this pantograph punch machine. We'll zoom in on that card. What a card was in Hollerith's system was a set of field sets, each field set containing a number of radio buttons. And the radio button would be on if it had a hole punched in it, and it would be off if it didn't. So in that way, he can encode a lot of information on one card and do it very efficiently. Then he had his tabulating machine, which was in two parts. There was the main part that had the dials that did the counting, and then the sorting cabinet. So the operator would take a card, put it in the machine, push down an array of pins, and if the pins went through a hole, they would touch a pool of mercury, completing a circuit, which would then cause one of the dials to advance, and would also open up one of the drawers on the sorting machine, and then you drop the card in, and then get the next card and do it again. And so it seems really tedious, but it was a whole lot better than the previous system, which was all done with paper and pen. The census was successful, and then Hollerith went on with other inventors as well to apply this to business. So well into the 70s, IBM and other companies were still operating this kind of equipment. Very, very successful. This is an accounting machine. Did everything that the previous machine did, but it's more automated in that you can put a whole deck of cards into it and run them all through at once. You didn't have to have someone feeding it one card at a time. Here's another example of its operation. So this is a card. In fact, this is a card. This is what they look like. The form factor of the card was based on the size of the dollar bill at the time. Hollerith chose that because there were lots of off-the-shelf stacking trays that you could just put these into, and so that reduced some of his engineering cost. In a later phase of the card, the way information was stored on it was reorganized. So instead of the random set of field sets that we saw before, it became a simpler column and row situation. So there are 80 columns on the card, each column containing 12 punches, or potentially 12 punches. So has anyone ever heard of the 80 character limit? We still have that today. You probably wondered, where did that come from? Why 80? Why an 80 limit? This is the limit. You can't put more than 80 characters on one of these cards. So this has been obsolete for a long, long, long time, but we still have the 80 character limit. So this card shows the Hollerith code. So the first 10 punches show how you encode a number. So digit 0 is the 0 punch, 1 is the 1 punch, and so on. To do letters, using what is called the Hollerith code, you take 1 punch from the top 3, and that's sometimes called the zone, and then 1 punch of the lower 9. 3 times 9 is 27. There are 26 letters, so it just fits nicely. There's one code left over, and the code that was left over was the 0-1 punch. It was decided not to use that one because you had 2 punches that were next to each other, and the machines could sometimes get a little brutal and tear away that little piece of paper and damage the card. The use of these machines to run business was called unit record management, and it was really, really successful. This is what allowed the modern corporation to evolve. Without this kind of data processing equipment, corporations just could not have become big. They could only have been as big as their bookkeepers could have managed. And these cards were used for everything. You'd have a card representing an account, a customer, an order, an invoice, a payment, a detail item in any of those things, a personnel record. In some cases, they were sent directly to the people at home. For example, you would get a bill from a company, and they would send along a card. And you would send the card back with payment, and when it received, an operator would punch how much you paid onto the card and then put it back into the system. The problem with these is that they're really fragile. And so you're giving this important data record to your customer, sending it through the mail and then getting it back. And so they very often came with instructions on them such as do not fold, spindle, or mutilate, telling people not to mess these up, because if they did, they could make life extremely difficult for the operators. This is a key punch machine. This is a more modern way of making cards. IBM built these well into the 70s, I think. In fact, my very first experience in programming was with one of these in the basement of the library of San Francisco State University. The way you managed to program on these things was your program would be a deck of cards, 1 card per statement or per line of your program. And if you wanted to modify your program, you had to go through the deck, find the card you wanted to change, pull it out, put it in the machine, dupe it, modify it, replace it, put it back in, and so on. If you want to rearrange lines in your program, you actually pulled cards out and reordered them. Extremely fragile way of putting programs together. And over time, you learned some gymnastic tricks to try to make it easier. For example, if you wanted to take a card and make another one in which you deleted some of the characters, the way you do that, first, there are 2 card stations on the machine. There's the read station and the write station. So you're always punching at the write station. If there's a card in the read station and you push the dupe button, then it reads whatever is at that column and punches it on the next one and advances both cards. If you want to do a deletion, you hold your thumb down on the card in the read station so it can't advance and push spacebar a couple times to advance the other one. Really nasty stuff, but that's how you did it. So the punch card was an amazing device. It served the purpose of memory, which eventually got replaced with RAM and core. It was storage, which eventually got replaced with disk. It was archive. You know, if you wanted to keep something for a long time, you would send a box of cards to the salt mine, and you keep that there. Eventually, we found better ways of doing that, but I'm sure deep underground somewhere you can find lots and lots of punched cards. It was network. If you were at the field office and you needed to get some records back to headquarters, you'd take a deck of cards and you'd put them on a train, and they would get sent back. Eventually, we figured out we could use wires to do that, and that got a lot better, but for a time, the way you did that was you'd mail a box of cards. The last of the functions to finally get replaced was user interface. Cards were used for user interface long after these other functions went away. You would have thought that'd be the first to go away because that's the thing it does worst, but it actually happened in the other order. The accounting machines were programmable, and they were programmed in a data flow sort of way in which you'd have a bunch of data sources, which could be columns on cards, and then you could direct them to registers and to calculation units and to sinks like the card punch or the printer. And so your program would be on a punch card or a punch board, and you could replace boards, and that would change the program in the machine. These were invented fairly early in the 20th century and remained current for a long, long time. For a long time, this was how you did programming. You've heard of spaghetti code? This is where it was invented. Eventually, these unit record machines were replaced by mainframes, by digital computers. They came online after World War II. There was a lot of research during the war in cryptography and weapons development, and when the war was over, a lot of that stuff spilled out into the commercial sector, and a surprisingly large number of companies started building computers. It was really obvious that that was the way a lot of things are going to be done going forward. Even so, these machines started coming online publicly in the late 40s, early 50s, and well into the 60s. Unit record machines continued to work into the 70s. So just because the good new technology is available doesn't immediately displace the crappy old technology. These computers were based on the stored program concept, which said that instead of having a plug board or some other external programming source, the program is stored in the same memory as the data. And there are going to be some really interesting implications for that. The chief one was that over time, the program may modify itself in order to change or improve its behavior. And eventually, after a large enough series of modifications, the program will become intelligent and perhaps even conscious, and eventually become our masters. And that would be a good thing. And so there's a lot of research into artificial intelligence to try to bring that about. Unfortunately, it didn't come about because the way our brains work is just way harder than we can imagine. You'd think if our brains worked right, we would be able to imagine how we work, but we don't. So instead, we had to program them a different way. And we came up with assembly language. First, we had to use machine codes, where there'd be a digit for each thing that the machine knew how to do, and a bunch of digits for each cell in memory. That was just way too hard to organize. So the first software tool, the first program to make programming easier was the assembler, and using something called assembly language. We don't know why it's called assembly language. The word assembly doesn't make any sense there. From what I've been able to figure out, the early programs did a lot of things. They would do things that we now call linkers and binders and loaders and other things. Those all happened in one program. And eventually those features got teased out into other applications, but the word assembly was left on the one thing they did that had nothing to do with assembly. But we still call it that. So here we've got a hypothetical machine. In the left column, we have statement labels. We're going to load the accumulator with whatever word is at the interx variable. We'll then subtract from that the variable called count4. Then we'll skip if the result was 0. If we didn't skip, we will jump to abort 27. And if we did skip, we will jump to a subroutine called calc-khj. That JSR is probably the most important instruction in the machine. It was early on very quickly recognized that the set of opcodes that the machine provides is just never going to be adequate for all the things we want to do. So we want to be able to create our own opcodes. And that's what the jump to subroutine did. It would jump to a piece of code, and when that piece of code was finished, it would then jump back. And there were lots of different ways that a machine could do that. One was it would remember the address of that instruction and put that in a register someplace so that when we came back, we could use that register to find out where the program resumes. Another way it could be done is that the program modifies itself. It will take a location in memory and change it to be a jump instruction to the place where we want to resume. And then when the subroutine's done, we'll jump to that instruction. Much later, the stack was discovered, in which we have a place in memory where we can keep track of those addresses, and that's much more convenient. So we see a lot of that in modern machines, but it came much later. So all throughout the mainframe period, we saw enormous architectural variety. There were a lot of really clever people building machines. Often you'd have multiple architectures within each manufacturing company. I don't know how many different models of computers IBM made, but during the early years, there were a lot of them, and there were lots of smaller competitors who had at least as many, sometimes more. They varied on things like word size, number types, like would they use signed magnitude or one's complement or two's complement, how many registers they would have, whether they were special purpose or general purpose. They might have base registers or index registers. Enormous variety in instruction sets. It was an amazing period, and all the machines were, machine designers were learning from each other. Brilliant, brilliant work done for many, many years. Basically trying to drive the price performance thing, because these machines were extremely difficult to make, and so they were trying to figure out what the best way of putting them together was so you could get the most work out of them. So here's an example of a mainframe. In the front left, we've got the disk drives. They probably couldn't contain as much information as whatever you've got in your pocket right now, but that was the main online storage in its day. Behind them, we've got the punch card equipment, the punch card reader, and the punch card puncher. Behind that, we've got the disk drives, and way in the back, we've got the memory cabinet. You might have 8K or so in a box about the size of a refrigerator, and as many of those as you could afford, that's how much memory your computer had. Then in the middle there is the console, which is where the operator works. Here's another one, another IBM computer. I mean, check out the console. The console has lots and lots of lights on it, lots of switches and buttons and knobs. That was the thing I was hoping to build. And if you were a programmer, that's really where you wanted to be working, because you, sitting there, you could see the contents of every register if you could read binary. That they had a light for each bit, and if you could work that out, then you could see exactly what was happening in the machine. You could single step the machine, full debugger there. The problem was they never let programmers in the room because they didn't trust them, and also the machine time was just so expensive. You had to justify the cost of this extremely expensive machine and plant. You just couldn't afford to have the downtime that a programmer would have sitting there, trying to single step through his program. Also notice the great Mad Men fashions that were in vogue at the time. This was maybe my favorite machine of that era. This is the Control Data 66000. It, designed by Seymour Cray, was for a time the fastest computer in the world. The thing I liked most about it was the console. Instead of all the lights and buttons, it had a simple keyboard and two round CRTs. So it could do real-time displays. Really, really nice looking machine. So it was too expensive to let programmers sit down at the console and do work. So the way most programs worked was in batch mode, where you would take your job and you'd make it in the form of a deck of cards, where the first card would be the job card, which identified what you were doing, and you might have an account card, and then a card to tell the operator what tapes to mount. and then a card indicating that you wanted the Fortran compiler, and then you'd have your Fortran program, and then an end-of-file card, and then your data, and then another end-of-file card, and end-of-job card. You take all of that, and you'd put it in a tray, and then you'd wait a couple hours. Eventually, a number of jobs would get put into the tray, and an operator would get around to taking them all out and taking the rubber bands off and putting them in the card reader, and they'd all get read into disk, and then they would take the jobs one by one, or sometimes several if it was a multi-processing machine, and run them. And the results will go to the line printer, and then the operator will take all the decks and put the rubber bands back on and match them with the printouts and put them in a bin. And so you come back a couple hours later and you pull the thing out and found out you're missing a comma. You go, okay. Then you get back to the key punch machine and you fix that comma and submit it, and the next day you found out that you missed another comma. So it was a really unproductive way of getting things done. They call the process submission. When you would submit a job, and it was submit in both senses. So there was an ideal way that the analysts thought that this process would work. First, the analyst would write the specifications and draw the flowcharts that describe the application. Then the programmer would code a program, probably into assembly language, based on the flowcharts. He would hand his coding pages to a key puncher. The key puncher would then sit at the key punch machine and punch them in. And just in case the key puncher made a mistake, they would take that deck and give it, and the coding forms, and give it to a second key puncher who's working at a slightly modified key punch machine called a verify machine. Retype everything, and if any character mismatches, the card is destroyed, and then it has to be repunched. Then, assuming it gets through that process, it's given to the operator, and then the operator will run it. And if there's a bug, then you call a meeting, because nobody is in charge of the whole thing. I can't imagine that this ever worked, but this was the official way that was documented. So what's a bug? So bugs, as far as I can tell, were invented by Thomas Edison. He invented a lot of other stuff. He also invented the bug. And this is the documentation, a story from the Pall Mall Gazette in 1889. Mr. Edison, I was informed, had been up the 2 previous nights discovering a bug in his phonograph. His phonograph was a device which would record sound and recover sound from a cylinder and a stylus. And so the friction against the stylus would either create grooves or produce sounds as it followed the groove. And I suspect that Mr. Edison's machine had a chirp in it that sounded something like crickets or something, and he couldn't figure out where the noise was coming from. But it was bugs. And so it was a sort of a standing American joke for a long time about the crazy inventor who will become wealthy once he can get the bugs out of his invention. A real bug was discovered by Grace Hopper. During World War II, she was working on ballistics tables for the military. And one day, their calculator stopped working, and so they opened up panel F, and they found a moth smashed in a relay. So she pulled it out and put it in her notebook with the notation, first actual case of bug being found. Her notebook is now in the Smithsonian. We'll get back to Grace in a little while. So the batch mode was not good for programmers. It was designed specifically to try to optimize the use of machine time, not to optimize the use of human time. So another mode was developed called time sharing, in which you'd have lots of users who could use the machine simultaneously. Each would get a fraction of the resources of the machine, but if the applications are interactive enough, each person gets the appearance that they've got use of a whole machine. And that turns out to be much, much better. And the way that you accessed it was through a device that was a whole lot less interesting than the console, but was good enough. And that was a teletype machine. This is a Model 33 teletype. It's an uppercase only system, and it can work online and offline. Offline means that instead of sending characters to a computer, you're sending them to its local paper tape punch. So sometimes online time was too expensive, so you could type your program in offline, and then when it was ready, you would log in and then have it read your paper tape, and that way you reduce your connect time charges. Now, program preparation on paper tape is even harder than on punch cards, because if you make a mistake, you can't throw that card away and replace it. It's one continuous band. One affordance that it did provide was there is a backspace button on the punch, and when you pushed that, the punch would go back one character. You could then push the delete button, and the code for delete is all ones, so go jink and completely punch out whatever was in that column. And the convention was that if the mainframe saw a code which was all punched out, that meant that you had deleted that code and that it should just ignore it. So if you're ever wondering why does your terminal have both a backspace and a delete button, this is why. The teletype was really slow. It printed at 10 characters a second. So you had to be pretty economical in terms of what kind of information you want to give to the user. In terms of accessibility, this is probably the best system we ever had, the one that gave the best parity between sighted people and blind people. You could take a voice synthesizer like the Votrax and put it on the line between the computer and the terminal, and it will say the name of every character that comes down the wire. And so a blind person can be aware of everything that comes out, gets exactly the same information that a sighted person should. In the years later, we made lots of advancements in terms of the way you can use machines, which have all tended to work very badly against blind people. So everything I'm about to say after this point works against them. So the character set used by the terminal was ASCII. In fact, for the Model 33, it was what I called half ASCII, because it was only uppercase. Eventually, machines allowed us to do lowercase, and the ASCII set recognized that. It contained 128 characters, which was just enough to do English. So as a typewriter replacement, it had pretty much all the keys and characters that a typewriter would have. For people with other languages, though, it was not adequate. And so there was for people in other countries using other languages, they would replace some characters. And that made it very difficult for doing interoperation between one country and another. Also for Asian countries, the 7-bit thing didn't work at all, and so they had to come up with double byte character sets, which made things even more difficult. Finally, that was solved with Unicode. Unicode attempted to take all of the national character sets and combine them into one character set. Really brilliant thing. And then later, Thomson gave us UTF-8, which was an 8-bit encoding, which was ideal for devices like teletypes and everything else we do. So today we've got UTF-8, which should be the one way that all characters are transmitted on the network. But just because we have the best possible one way doesn't mean that everybody's doing that yet. One thing that is odd about ASCII is it has a carriage return character and a line feed character. This was to model the way that teletypes actually worked, where the carriage return character would take the print element and push it over to the left. And the line feed character would take the platen and spin it one line. And so most lines are going to end with going back and rolling the paper. And it took 2 separate codes to do that. Most time-sharing systems didn't require people to type in both codes. Generally, they would allow people to hit the return key, and then they would echo the line space key, just because there's no reason to make people type both characters. And also, other devices don't work that way. Most other printers of the time would just take a line of text and print it in advance. There was no way to separate the carriage return from the line feed function. So this was a pretty device-specific thing. And so most systems who adopted ASCII as their character set chose one or the other. And the systems that tended to be more hardware-focused in their orientation tended to pick line feed, and the systems that tended to be more human-focused tended to pick carriage return. And that was fine until they needed to interoperate. And so then you have a committee of people, some using line feed, some using carriage return. How do you resolve that? You could just pick one. You could even flip a coin because it really doesn't matter. But these committees could not decide. Nobody wanted to be the guy who got it wrong. Nobody wanted to be the guy who had to change. So they came up with a mutually disagreeable compromise, which is we will always require both. So that's the way the internet protocols work. We haven't been using teletype machines in I don't know how many years. They're decades obsolete. But we're still forcing both sets of control codes to be transmitted in HTTP because of this teletype heritage. So I would get into arguments with guys in the basement at the computer center. On our campus, we had teletype machines, so we could do time sharing, and we also had the batch system. And we would argue about which was better. And it's obvious that the time sharing system was better. It was designed to use human time more effectively. It was just the right thing to do. And in fact, everything we're doing today looks much more like time sharing than it does like batch. So history bears us out. But there were people there who were vigorously arguing that batch mode was the right way to do it. That time sharing was a fad, that I'm trying to think of what their arguments were. They didn't make any sense at all. The main one came down to discipline, that the discipline that batch mode required, where you had to think the whole thing through and submit flawless programs to the computer, because if it was buggy, you'd never ever going to get it work. And so that call to discipline was the biggest advantage of batch mode. So it was another example of where you have a technology that was developed by programmers for programmers, and there were programmers who were rejecting it and thought that they were well-reasoned in their rejection. And what it really was, when you scrape it all the way down, was while they intellectually understood what time sharing did, they had never tried it, and they never understood it. And so they assumed that they were being very successful in their current endeavors without ever having understood that. So therefore, it was not important to understand that. Therefore, they could argue or out of hand reject any argument that required that understanding. And I continue to see that happening over and over again through pretty much everything that we do. One of the big benefits of time sharing was that it provided the first social network. So all of these innovations happened first in time sharing. File sharing, email, distributed computing, computing as a service, chat, blogs, open source development. That all happened on the mainframes a long time ago. We think this is all fairly current stuff. In a few minutes, I'll show you why we think it's current stuff. But this stuff all happened back in the 60s and 70s. We had games on the mainframes, both single-player and multiplayer games. It turns out games are a really important place for technology development. There's some really good work in terms of user interface design, program construction, algorithm development, was all motivated by games. And then finally, security. The mainframes had a huge, or the time-sharing systems had a huge security problem because they had lots of people running programs in the same memory. And integrity demanded that they be able to keep all of that stuff separate and not interfere with each other. So there was a lot of work in that era to try to figure out how to do that, and then to try to do the even harder thing after that, which was to allow those programs to sometimes cooperate. Because we started to identify the need for collaborative applications. And the time-sharing machines were just starting to figure that stuff out when they were destroyed. Now, one of the other things that happens in time sharing is you need an editor. And a paper tape editor doesn't make it. You need to be able to edit online. And you can't do what you did with cards, take a card out and change it and put it back. So they wrote programs which allow you to do that. where you could load a file and then go to a particular line in the file, replace that file, insert some more lines after that line, and so on. So almost every system had an edit program in it, or it might have been called ED or QED or some variation on that. But everybody had one. At MIT, they called it TICO. And they then figured out how to add keyboard macros to it, and that became Emacs. And VI also came out of edit. So, and these text editors are still in wide use, still very popular. They are dinosaurs left over from the time-sharing era. The next step was replacing the teletype with CRT terminals. CRT terminals were eventually much cheaper. They used less paper. And eventually they allowed for on-screen editing in which they could display a page of information and you could cursor around on it. For example, this terminal had some arrow keys on some of the letters to help in designing software that would do that. If any of you are VI users and ever wondered how could it possibly ever made sense for H to go that way and L to go that way, this is where it happened. Again, this is a time-sharing era dinosaur which still exists in the current age. Now, IBM was never able to get time-sharing right. Time-sharing requires that you be able to switch from one process to another on a keystroke basis, and their software was just not adequate to do it. So rather than fix their software architecture, they invented a new piece of hardware that they called the 3270. At the time, they called it an intelligent terminal. Today, we'd probably call it something else. And the way that 3270 worked was you would take a page of data and whip it down from the mainframe into the terminal, and it would show up on the screen. And some of the screen will be full of characters, which are part of the display, and some of the characters are reserved as fields. And so the user can then type stuff directly into the field locally, and then hit the submit button, and then all the data in those fields gets sent back to the mainframe. Does that sound at all familiar to anybody? Does that sound, like a form application? This is where that came from. When the World Wide Web came up, there were a bunch of dinosaurs who said, oh yeah, I remember that. And that's how we got a lot of what we've got today. Now, while all of that was going on, one of the smartest guys who's ever lived, Doug Engelbart, was working at SRI on the Human Augmentation Project. Like me, he early on recognized the potential of computers, but unlike me, he was able to do some really, really important work on it, which he demonstrated in 1968 at the Joint Computer Conference. It was the most amazing demo anybody had ever seen. He demonstrated hypertext. He demonstrated on-screen displays. He demonstrated groupware. He demonstrated video conferencing. He to-do lists, and outline processing. Just goes on and on and on, all these things that he wasn't just theorizing, that he was doing and showing live. The only thing anybody paid attention to was the mouse. He also invented the mouse, and he demonstrated that as part of this demo. He also had a chording keyboard where he had 5 keys that he could play like a piano and do keys very quickly that way. He had 5 buttons here, 3 on the mouse. He could type ASCII with both hands while he was moving. His theory was, let me take a couple hours to train somebody in the system, and I can allow them to do amazing things, be incredibly effective. The world decided it didn't want to work that hard. But just amazing what he did. His lab was one of the first 2 sites on the ARPANET, which eventually grew to consume all of the networks on the world. At the time he was doing this, everybody else was on punch cards. You just can't imagine what a profound shock this was to see him showing the future in San Francisco like that. So I highly recommend you see it. It's available on YouTube. Go search for Doug Engelbart, for the mother of all demos. It's out there. It's just amazing. We still have not caught up to all of Engelbart's vision. And what a number of people have done over time is take some little bit of what Engelbart was doing but hasn't been fully adopted yet and work on that. And Some people have gotten rich and famous doing that. And there's still a lot that Engelbart was doing that we haven't caught up to yet. You can do that too. Highly, highly recommend that you check out Engelbart. Okay, so next, mini computers. There were a number of developments that allowed for repackaging some of the stuff that had been in the mainframes into a much smaller, less expensive form factor. And these became mini computers, and a whole new class of companies started making these. Companies like Digital Equipment and Data General, Basic 4, a bunch of them. And created many new markets for computers. In some cases, they went into companies who already had mainframes, but there would be operations within them who found that the data processing departments were not responsive to them. You know, when they first got the computers, it was great. Now we can do things because we have computers. And then a little, not surprisingly a short time after that is, we can't do these things because we have computers. And so people would try to get around the system by finding some cheap box that they could put in their own department. In some cases, they would end up in small businesses and in small colleges and places that formerly hadn't been able to afford computers at all. They started to show up in places that were new. And again, we saw an explosion in CPU architecture. An amazing amount of creativity in the way that the designers and engineers came up with to get work out of these amazing little machines. The next step was microcomputers. And this began in a collaborative project between a memory startup called Intel and a company that was making intelligent terminals, similar to the ones we saw earlier, called DataPoint. DataPoint at that time was making their terminals completely out of discrete components, and they were kind of expensive, and they also got really hot because all of those components created a lot of heat. So they came up with a design for a little CPU, and they figured if they had that CPU, they could reduce the part count on their terminal significantly, make it a lot cheaper, and make it work better. And so you'd run a little program inside that little chip that would look at the keyboard and look to see if anything's being pressed, and look at the serial port and see if any characters are coming in. And based on what it's finding, it would cause things to happen and then put them on the screen or send them on the wire. So Intel developed a device called the 8008, and DataPoint was very successful with that, and they also sold it to the public, and they were also very successful with that. And it then got improved into something called the 8080, and then another startup that spun out of Intel called Zilog improved it again and called it the Z80. In addition to that family, Motorola had the 6800. There was another chip called the 6502, which was kind of based on that design, but was much, much cheaper. And so we started seeing an explosion now in 8-bit CPU architecture. And they went into all kinds of devices, including into computers. So the Apple II had a 6502 in it. And it was the Apple II that put an end to time sharing, because the economies of personal computing were just so overwhelmingly better than what you could get with a time sharing system. There were some trade-offs in that you didn't have access to the network anymore, but if all you wanted to do was to compute some models, you could do it much cheaper on an Apple II than you could through a time sharing bureau. This is the register set for the Z80. It had several 8-bit registers, A, B, C, D, E, H, and L. It had two 16-bit index registers, I, X, and I, Y. It had a stack pointer that was also 16 bits and a program counter. And all Z80s had this, and was a very nice way of writing programs in assembly language. Back up just a little bit. No, I'm not going to back up. We'll do that later. So there was then the 16-bit generation. And again, a number of companies came up with very interesting designs. Motorola, the 68000, Zilog, the Z8000, National Semiconductor, the 32000, which I think was the best of that generation in terms of instruction set elegance. If you were writing a code generator, or if you had to write an assembly language, which you shouldn't anymore by this time, but if you had to, it was clearly the best thought out of all of them. Intel went in a different direction than the others, though. They came up with an architecture called the 432, which they called a micro mainframe, where they tried to push a whole lot of the functionality that you would expect to find in an operating system, push it all the way down into the silicon. So garbage collection would be happening in the CPU transparently. And they designed it to be programmed exclusively in high-level languages, primarily Ada. They took Ada, which was a language being developed for the Defense Department, and extended it to make it object-oriented. And so they had that support in their CPU. Very forward-looking design. It was one of these designs which just went wild with all the things that they could do. And they never properly accounted for the cost of all the things that they were doing. And so the basic CPU ended up having to be split onto 2 chips because it was too big to put on one. And it turned out to be really, really slow. So it was very expensive, very slow. It turned out that people couldn't figure out how to write programs for it. And it was a total disaster for Intel. And it looked like they were going to miss out on the 16-bit generation. They were probably going to go out of business completely. So they had to very quickly figure out, how do we get into the 16-bit race, having stumbled so badly on the 432? So they decided to go back to the 8080, which had been and continued to be a big success for them, and try to capture the business of the 8 bits by making a machine that was assembly language compatible with the new one. So this is a contrast of the Z80 register set and the 8086 register set. Very, very similar. They changed some of the names of things, but basically it's very easy to see the Z80 heritage in the 86 instruction set. So they very quickly threw this thing together, tossed it out into the market. They didn't design it to be good, they designed it to be compatible. It turned out that compatibility didn't really matter. The thing that ultimately sold it was cheap. So it went into devices like this one, the IBM PC. IBM had looked at what Apple was doing, the effect Apple was having on their mainframes. They decided they needed to get into the personal computer business, and they built the machine and called it the personal computer, sort of took over the space. And they put Intel's chip in it. Then they went to a company that was best known for its crappy BASIC interpreter, a company that knew nothing about operating systems, and got them to make an operating system for them. That was MS-DOS, and that went into that machine. There are a lot of other companies who also made similar machines, and most of them failed. The only ones who succeeded made machines that were exactly the same as this machine, what were called clones. And the clones set the new standard for cheap computers ever since. That was followed by another generation, the 32-bit generation. And there were lots of really elegant designs out there that were really good. Intel, again, decided to play compatibility. So for the 386, they put in a mode which simply took each of the existing registers and changed its size from 16 to 32 bits. And this was done again in the 64-bit generation. AMD, this time doing the design, took each of the Z80 registers and pushed them into 64 bits. Without question, the worst CPU architecture we have is the Intel architecture. And Intel has always been very much aware of this and embarrassed by it. It improved a little with each generation. The 386 is significantly better than the 286, but still at its root, there's still an 8080 in there. And there's just a lot of awfulness as a result of that. So to manage its embarrassment, Intel has pursued a lot of other architectures that were actually quite elegant. There was the 960, which was really good. There was the 860, which was also very good, and the Iridium. But the market said, no, we don't want that. We want the bad stuff. We want the compatible stuff. And who is making those decisions? It's programmers. Programmers say, no, we don't want the machine that is best for programmers. We want the crappy one, because that's what we're used to. That's the way we do it. So even though we think we're very knowledgeable about the work that we do, as a community, we are historically quite bad at understanding what we do and what we need in order to do what we do effectively. One of the reasons why microprocessors ended up destroying the mainframes and the mini computers and eventually became everything was because of a prediction made by Gordon Moore, who was at Intel. He said that he hypothesized that the complexity for minimum component costs has increased at a rate of roughly a factor of 2 per year. He just assumed that that would go on, perhaps at a slightly slower rate. And he thought it would go on for 10 years. It's gone on for like 40 years now. It's just amazing that for every 2 years we get a doubling in the efficiency of semiconductors. And this prediction was called Moore's Law. And it has held for an amazingly long time and is likely to continue to go for a while further. It's not really a law, it's a prediction that became a self-fulfilling prophecy. You know, if you're an engineer at Intel, you're shown a point on his graph and said, this is where you need to be in 3 years. Come back when you can hit that point. And they have to do amazing superhero kinds of stunts in order to accomplish that level of performance. And when they turn that in, it's like, yeah, okay, we knew you were going to do that. You know, it's nothing special. It seems to me pretty thankless to be doing that kind of engineering at Intel. So it can't hold forever. Everybody knows that eventually Moore's Law is going to fail, but it's still holding, and so it's got a lot of life in it yet. The other thing we've seen is an end to CPU innovation. We used to see a lot of really radical new designs happening all the time. We don't see that anymore. Basically, we've got 3 architectures that we use for most of our stuff. Virtually all the computers are in Intel. Most of the game platforms are on PowerPCs. Most of the mobile devices are on ARM. That's it. I mean, nobody's making new stuff, nothing radical. It's just refinements of stuff that's been happening for several decades. And we're doing even worse in operating systems. It used to be that every model of every machine had its own operating system. And that came with a lot of obvious inefficiency. And so we've pushed that down, and now we have just 2. We've got Unix, which was developed in the 70s, and we've got Windows that was developed in the 80s. And of the 2, Unix is obviously the better one. But there's no innovation happening in operating systems. Basically, we've been rewriting the same systems for 40 years. That's just not where we do innovation. Where we do innovation is in programming languages. And that's been going on for quite a long time. In the 50s, everything was assembly language, unless it was still punch boards, plug boards. That was still going on too. And there was interest in research in automatic programming because the perception was programming is just way too hard. We need to figure out a way to make it easier. So we'll make it easier by having the computer do most of the work for us. We'd already seen with assembly language a start to doing that. So we want to go further so that instead of writing a program, you instead tell the computer what the program's supposed to do, and then the computer will write the program for you. So, brilliant, that should be easy. So there was a lot of work and experimentation on that, and the result of that experimentation was called Fortran. You might be looking at Fortran and going, this looks kind of like a program, and in fact it is. Automatic programming didn't work. Because it turns out the description of a program in sufficient detail to do what you intended to do is still a program. What they succeeded in doing was raising the level of abstraction. So instead of dealing with memory cells and opcodes, we're now dealing with things which look more like the problem domain. And so you can be much more productive in this language, which is a really good thing. But this doesn't replace programming, it's just another kind of programming. And we've seen this happen over and over. Right now, there's a lot of interesting work happening in domain-specific languages. And there are some theorists who think that working in those very specific languages, you're not really programming, but in fact you are. You're just programming at a different level. And sometimes a more appropriate level, more productive level, which is good. So this is a Fortran program. Fortran arrived in the late 50s. And here we've got a subroutine. Subroutines are very similar to modern functions. Fortran didn't allow for recursion, but in other ways it's very much like our current functions. The if statement looks a little odd. What it means is if n is negative or 0, jump to statement 10. Otherwise, if it's greater, jump to statement, or if it's positive, jump to statement 8. Eventually, they came up with a better way of writing if statements. But even this if statement looks quite a lot like the C if statement, and that similarity is not accidental. It also has a do loop, which allows you to do something a certain number of times. So in this case, we will iterate from here to statement 9, each time varying I from 1 to n. That's how you read that statement. Then their data is taking the ith member of I. A square bracket hadn't been introduced into mainframes, and so that character wasn't available. So they used parentheses for doing that. But they did use the asterisk for multiplication. I don't know if you ever wondered why we do that, why we don't use an X or a dot or something else instead. The reason is that the early mainframe instruction sets didn't have those characters in them. They were designed for business applications. They had character sets that looked like typewriters, and so Fortran established the convention that you use asterisk to mean multiplication, and that's still the case in virtually all languages now. Another language was COBOL. COBOL was developed by Grace Hopper, who you remember earlier discovered the bug. COBOL was an attempt to make programs look more like English. At first, the hope was that anybody would be able to write business applications, and that turned out not to be the case. And then there was a secondary hope that, well, at least anybody ought to be able to read one of these programs and understand what it does. And this was particularly hoped for by management, because management had little trust or understanding of what programmers were doing. And the thought was, if they could read what they were doing, then it'd be a little easier to keep control over the operation. But that didn't really work either, because there's a lot of subtlety in programming in any language, which is not readily apparent to most people. BASIC was a slightly later language. It was designed specifically for time sharing. It was developed at Dartmouth University by Kemeny and Kurtz. They did a really clever thing. They started with Fortran and stripped it down until the simplest possible language, so that anybody who could use it without much training at all. It was very quick to learn. They also came up with a clever way of editing programs. They came up with the line number. And so you give every statement a line number. And if you want to change that statement, you simply type the line number again and the new statement that replaces it. And they used the same line number as the destination for jumps. So there's a certain kind of economy in there. So here we have a hello world game where at line 20, the program will print the string, what's your name, and then read from the terminal whatever you typed, followed by carriage return. BASIC, even though it was a really primitive language, had the best string processing, the best text processing of any language in its generation. And it hardly does anything, but it just does the right things. It's got a way of representing a literal string, a way of concatenating a few together, a way of teasing them apart, inputting them and printing them out. That's all you need, and it did that. And that's been followed by virtually every language since then. In that sense, BASIC was incredibly influential. The other thing BASIC did was it sort of crystallized the input-output relationship. So here, I want to interact with the user, so I will print and I will input, which means my program stops until the specific thing that I asked for is delivered by the user. So it's an extremely modal thing that the operator has to somehow figure out how to convince the program to get to the place where it wants to ask the thing that the user wants to tell. Later, we discovered that this was a really bad way to write programs, but it took a long time to figure that out. So BASIC influenced a number of other languages. There was Business Basic that ran on the small business mini computers, which added sort of database functionality to their file systems, so you could store values and retrieve values by keys into files and pull them out and do operations on them. It was much more pleasant than COBOL for most people, and it was very cheap and very popular. Microsoft was started on Microsoft Basic, and that eventually evolved into Visual Basic, which for a few years was the most popular programming language in the world, although it has been replaced by another that we'll get to a little bit later. A really important language which came out in 1960 was Algol 60. It is the best designed by committee in the history of programming languages. A bunch of really smart guys got together and came up with a language for use in expressing algorithms for publication. But while they were at it, they also made it actually work in practice. And so it defines a couple of languages, a reference language, a publication language, but it worked. And it was popular within its sphere. There were a number of machines that were designed specifically to use Algol as their basic language. It introduced the notion of structured programming and blocks. So we have blocks in modern programming languages. Most of them use curly braces. That came from Algol. Algol used the words begin and end instead of curly braces because, again, curly braces weren't available at that time. They were invented later. But that's where we got that stuff. It was an extremely important language, a very influential language, but unfortunately, there were lesser languages which tended to be much more popular. One big debate that happened, partially as a consequence of Algol, was the structured programming debate. Dijkstra wrote a famous letter titled, "Go To Considered Harmful." And Dijkstra claimed that programs like this are just too hard to follow. When they get complicated, you got the things bouncing here, there, there, there. You can't keep track of what the program's doing. It doesn't scale sufficiently well to allow us to write programs of sufficient complexity. And that we would be better off if we simply stopped using GoTo and used the other features that Algol had provided. It turned out he was right. But at the time, this was an extremely contentious idea, that programmers would have an easier time managing the complexity of their programs if they don't use this feature. Who was most enraged by this suggestion? Programmers. And so this debate went on literally for a decade, no, for 2 decades, for a generation, arguing about whether GoTo should be eliminated or not. And ultimately, we got rid of it, and that was the right thing to do. And I think it's not coincidental that it took a generation to do it, because basically we had to come up and train a whole new set of people who were not stuck in the previous idea. And again, who better should have understood the value of structuring your programs in such a way that they could scale better? Only programmers should understand the value of that argument, and programmers were the least able to understand that argument. Okay, so from that generation, Fortran, COBOL, and Algol, each of these languages was pretty specialized. In particular, Fortran was intended just for scientific processing, and COBOL was intended just for business processing. And there was interest in trying to make a common language that could do both. At that time, they didn't recognize that there were other things as well that would actually dwarf both of those applications, but it's still early yet. There was PL1 developed at IBM. There was the combined programming language that was developed in England, Algol 68 that was developed in Europe. All wanted to be the Uber language that would do everything. And all of these languages had some partial success, but none of them fulfilled the promise of being the language that would bind us all. So in fact, there was a reaction after that to try to scale it back and to come up with simpler languages. So there was a dialect of CPL called BCPL, Bootstrap or Basic CPL, which was a simplification, similar to what had happened with Basic and Fortran. Strip it down, make the simplest possible language that works, and then you've got a language that works. BCPL was very successful within its niche, and we'll see more of that in a moment. Then the design of Algol looked at what was happening in Algol 68 with horror and saying, no, that's not the way. Algol actually got it right. And there were some who considered Algol an improvement on most of its successors, which in fact was true. So taking that approach, Wirt came up with Pascal, which was extremely popular. He designed it as a teaching language, but a lot of people put it to work as a general programming language. Unfortunately, there were a couple of significant design problems which interfered with its larger mission. One was that it wasn't modular enough, so it assumed that a whole program was one unit, and that turned out not to work practically. A bigger problem was its type system. Types were intended to make programming easier, but in this case it made programming significantly harder because the dimension of array, the number of elements in an array, was considered part of its type. So if you wanted to write a function that could deal with an array, it could only deal with arrays of one fixed size. And that turned out not to work very well. BCPL inspired Ken Thompson to make another language called B, which basically took the good ideas that were in BCPL, but give them Fortran syntax, which wasn't necessarily an improvement, but he did. So we got that. And then C took B. This one was Dennis Ritchie, taking some of the good ideas in Pascal, being more selective in taking stuff from its type system, adding it to B, which was mainly a typeless language, and made C. C was incredibly popular, and it's become the most important implementation language of all. And virtually all languages since then are either based on C or are implemented in C. C has been an extremely successful language. So while all this is going on, there's still assembly language happening. And again, there's the debate, which should we be using, assembly language or high-level languages? And there are people arguing both sides, that the high-level languages make you much more productive, that the number of lines of code you can write in a day is pretty much constant. And if you're writing in a high-level language, those lines get more work done than in an assembly language. That's the basic argument for the high-level languages. The argument for assembly language was, yeah, but I don't know. There wasn't a good reason, but they'd argue about it, and they'd argue on and on and on and on. Now, it turned out there was a good reason for assembly language. You've got systems like this. This is the Atari 2600, the VCS video computer system. This is the first computer most people had in their house. It had a 6502 in it. It was really cheap, and it ran games that you could play on your TV set. And it was impossible to program this machine in any high-level language. You had to be working in assembly language, and I'll show you why. So the machine contained a 6502 CPU, actually a 6507, but it's the same instruction set, which had a very small number of registers. It had an 8-bit accumulator, 2 8-bit index registers, an 8-bit stack pointer, and a flags register, and a 16-bit program counter. That was it. That's all the registers you get. So there's no code generator that knows how to write efficient code with that. Worse than that, there was no software or firmware built into the console. So the only code there that could run was what was supplied on the game cartridge. People go to Sears, buy the cartridge, you plug it in, you play. The cartridge had 4K in it. That's not a misprint. 4,000 characters were on the cartridge. So all of your program, all of your static data, all of your visuals, bitmaps, text, everything's got to fit in that 4K. Later they came up with an 8K, but 8's not enough more than 4 to allow you to think about writing this in C. In addition, the console has some RAM in it. It has 128 bytes of RAM. Again, I'm saying this very precisely, 128 bytes. You can count them 1, 2, 3, up to 128, and that's all you get. That has to include all of the dynamic state of the game, including any dynamic bit of imagery that you're getting ready to hand to the video shift registers, any music that you're playing, you've got to be keeping track of the note list and the durations and all that stuff. That's got to be in RAM. Your stack your subroutine stack is in that same RAM. The guys who could write for the VCS were heroes. I mean, they would do amazing stuff. You know, there are like 30 variations in the tank cartridge. You know, you can toggle the console button and play like 30 variations of this game where these two guys go around and shoot at each other. And it was all implemented in 4K, and it's in color. And when the game's not going, they will cycle the colors on the TV so that you don't get burn-in on the phosphors on your set. All of that is happening in the cartridge. 4K, 128 bytes, amazing. So you had to do that in assembly language. There was just no way you could do it any other way. And the incentive is you can get your program in millions of homes. And so no, that's a good thing to do. And you can't get them there writing in Fortran. So specialized systems like this just weren't compatible with high-level languages. And so you have these throwbacks which kept assembly language being useful long after high-level languages became dominant. Algol went on and had some other influences. Algol was in 1960. 1967, Simula was developed in Norway. Simula was the first object-oriented language. Simula added classes and objects to Algol. That language had a big influence on Alan Kay, who went to Xerox PARC. And in 1982, he started working on a programming language for kids based on the object-oriented idea. And the name of the language was Smalltalk. Alan and his lab spent a lot of time working on this language. It went through several generations, a lot of testing, brilliant work, great implementations. They published it 8 years later, Algol, or Smalltalk 80. Great language, the first truly modern object-oriented language. They did it as part of motivation for a system that they're called the Dynabook, which was going to be a portable personal computer. And as part of that work, they took what Engelbart had been doing on time-sharing systems and applied it to personal computers. And so they adopted some things that Engelbart did, very obviously, things like mice and his approach to interactive displays. They took a little bit further. They came up with bitmap displays with overlapping windows. They invented window systems for that. Basically, the modern user interface was developed at Xerox as part of the Smalltalk project. They also at Smalltalk, or at Xerox at the same time, they came up with local area networking and Ethernet and laser printers and a whole lot of stuff that we take for granted today. Xerox tried to commercialize all this stuff, but never really understood what their labs had developed for them, and so those projects failed. Smalltalk itself looks a little alien. So here we've got a statement. We'll set the result to either greater, or the string greater, or the string less or equal, depending on the relation between A and B. And the way they would describe this working is they would send the greater than message to A, passing B as a parameter. And the result of that will be an object, which is either the true object or the false object. And depending on which it is, they will then call that object with the if true, if else method. And depending on what the state of the variable is, it'll call one or the other. They use this language where they'd say, instead of invoking a method, we haven't come up with that terminology yet, so they called it sending a message. And I don't know why it is, but a lot of programmers just couldn't get used to the syntax. We've got, what's going on there is really a method invocation, but it's not dot and a name and some parentheses. It's these keywords with colons and then values in between them. This is actually more readable if you understand what's going on, because it's self-documenting to the extent that it tells you what each parameter is doing, which is something that we don't have in the conventional notation, because all you have is a comma. It doesn't tell you what anything is. So this may be a superior notation, but it was profoundly rejected by who? By us, by the programmers, because we couldn't understand it. So as a consequence, Smalltalk never made it commercially. But despite that, Smalltalk has been extremely effective as an influencer. So under the influence of Smalltalk, we've seen C evolve into Objective-C, C++, and IFL, and then C++ inspired Java, which inspired C#. So basically every language since then has taken ideas from Smalltalk combined with the crappy syntax of C. And that's basically the modern world. And all this took a long time. So 1967, Simula, to 1995, Java, and now here, many years later, it took a while for object orientation to be just the way you do things. And again, there were debates. We don't need objects. Objects don't make sense. They're just a lot of overhead. They don't really do anything for you. Who was making those arguments? Programmers were making those arguments, thinking they knew what objects were, having no experience about what they are. But eventually, we all figured it out, and we took that next step forward. So software development comes in leaps, and our leaps are much farther apart than the hardware experiences. You know, Moore's law lets the hardware leap every 2 years. We leap more like every 20 years. And again, basically, we need a generation to retire before we can get the good new ideas going. So we tend to be, despite the fact that we're always talking about innovation and how we love innovation and we're always innovating, we tend to be extremely conservative in the way we adopt new technology. So Smalltalk had some other influences as well. One of them was a language called Self, which was also developed at Xerox PARC, eventually moved to Sun Labs, work done by Unger and Smith. Brilliant language, took the Smalltalk idea and took the classes out. So instead of having classes which define sets of instances, you just have the objects themselves, and you allow one object to inherit from another object. That greatly simplified the language. Part of their motivation for doing that was to allow them to go faster. They were trying to figure out how to make Smalltalk or a Smalltalk-like language run as fast as C. So the thing we know Self best for is the stuff that they did in performance. They did amazing work in garbage collection systems, like generational scavenging came out of this language. The hotspot technology that made Java acceptable came out of the Self project. The V8 system that's being used at Google also came out of the Self project. So Self was a big influence on performance. But also it did a really good job of demonstrating the idea of prototypes, where you don't need a class, you simply have an object that inherits from an object. That turns out to be a really powerful idea. It's a newer, more recent idea than classical object orientation, which is why the idea was rejected out of hand by most programmers, because again, it's new and unfamiliar, and if I don't know about it and I'm such a hotshot guy, then it can't be important. But it turned out it's very important, and we saw it first in Self. Brings us to the object model, or the actor model. This is another kind of indirect spin-off from Smalltalk. So Smalltalk would talk about you send a message to an object. Carl Hewitt at MIT listened to the way they were describing it and going, well, that's not what you're doing. These are just invocations. You're not sending a message. But what if you were sending a message? What if each of these objects was an independent process? Let's call it an actor. And the only way that they can communicate with each other is to send messages. And so the messages will be asynchronous. You just send the message like you're sending an email. And every actor will have a queue of incoming messages that it can then process in order. What kind of programming model would you have? And it turns out you have a model with really interesting properties. It scales really well because you can take all these things and put them on one CPU or put them on 1 million CPUs and they work exactly the same. It also had really interesting security properties in that each of these was a separate process that was completely sealed, so nothing could interfere with it, so they all protect their boundaries. Any actor can only talk to other actors that it has knowledge of. If it doesn't know their address, it can't send them an email. And so it beautifully demonstrated the capability principle. So is really good stuff. And it turns out, if we kind of step back from things, a lot of things that we're already familiar with are already in the actor model. For example, modern desktop applications are all built around an event loop. That event loop looks very much like the message queue that an actor would have. So an application is an actor. Looking at the web, a web service is an actor. It's something you send it a message, and it may send you a message. So the actor model is more familiar than we may realize, but it was still pretty new and again, too radical for most programmers. But there were a couple of programmers at MIT who wanted to understand it better. So they took Hewitt's actor model and implemented a part of it in Lisp, in creating another language that looked a lot like Lisp but had slightly different semantics. And the thing that they discovered was the actor dispatch model looked exactly like their function dispatch model, that functions and messages were the same thing, which completely surprised them. They weren't expecting that at all. So they kind of refined that idea and came up with a language called Scheme, which is sort of the perfection of Lisp. Lisp was the artificial intelligence language that had been developed at MIT in 1958, and they got it right. And part of what happened was they needed tail recursion in order to allow you to keep calling things and never expect them to return without running out of memory. And it also allowed for lexical closure, so that if a function is nested inside of another function, it gets access to everything that the outer function has, even if the outer function is already returned. So there are all these really intricate nested actor patterns that fell out of the work. Really brilliant stuff. The scheme then went on to influence a lot of language designers, also influenced Lisp. So Common Lisp owes a lot to things that Scheme figured out. The actor model also influenced the design of a data flow language called Joule. Joule had been designed specifically for security applications. There was then another project that took Joule, gave it Java syntax, and created a new language called E. And E is the language that demonstrates the object capability model, which turns out to be the savior of secure systems going forward. So there's a lot of work now in trying to make JavaScript into a secure language that's all deeply informed by the work that happened at E. You may have heard of Kaha. It's something that we're using here at Yahoo in order to secure our applications. Kaha was developed at Google based on work that had happened in E. Okay, let's take a little detour now. So Xerox had done this brilliant work with the Smalltalk and the Dynabook and was unable to commercialize it. Steve Jobs got a demo of it and immediately understood the potential of this stuff. So he took it back to Apple, and eventually Apple produced a device called the Macintosh. It had a 68,000 processor in it, 128 kilobytes of RAM, so it was 1,000 times better than a VCS, but was still too small. So initially you couldn't program this machine in anything but assembly language. But it had the bitmap displays and a mouse and a lot of the stuff that had been demonstrated at Xerox. So, but it was still hard to program. And particularly for programmers who were used to the basic model where you input and print, you don't do that on this device because the program has to be running all the time. The user has to be able to click anywhere and have it be meaningful. So the old stop and wait for input model just doesn't work. And Apple gave people advice on how to write their applications, but it was really difficult to get programmers doing that. So Bill Atkinson came up with a really interesting application. He had written Mac Paint and QuickDraw. He came up with this little database tool, which he thought was going to make it easy for people to make applications. And they added a little scripting language to it, and then suddenly the stuff that had been so difficult about Mac programming suddenly became easy enough that non-programmers could do it. And that was called HyperCard. For a while, HyperCard was free on all Macintoshes, and it was extremely successful. It was imagined to be the future of software, that all applications from this point on were going to be HyperCard stacks. HyperCard was going to be the way everything was going to be made going forward. So what is HyperCard? HyperCard is basically a file format of stuff that can be displayed visually, and it has a very small set of types in it. There is the stack, which can contain any number of backgrounds and cards. There's a background which contains an image and maybe some buttons and fields that get shared by every card that has that background. You can have cards which can use one of those backgrounds and can also have buttons and fields on it. And a button is a clickable area, and it can have text or image, and a field is a thing that has text that you can type into. So many of these things we have on web pages, but this was an earlier model. And the whole thing works as a little IDE, in that you could type in Command B, and that would make a new button and open up a dialog, and then you could give the button a name, and you could configure it to have it tell you what kind of input it was going to be. And you could also then click on its link, and that would take you to another page in which you can set its script. What did its script look like? Well, script could look something like this. You'd say on mouse up, and some of you might be going, whoa, on mouse up, that sounds eerily familiar. This is where all that stuff came from. So this, HyperTalk wanted to look like English. Their motivation was a little bit different than COBOL's, but similar. So they wanted to make the language easy to teach by making it look familiar. So here we say, set the location of card button X to pause. In a modern language, we'd probably write something like card.button sub X equal pause. Both would do the same thing, but that's how you write it in HyperTalk. So HyperTalk is trying to look wordy. One of the disadvantages of HyperTalk is that you can't ever see the whole program, because all the handlers are nested inside of their individual components. So you never get the big overview. But the plus side of that is, because everything's a trade-off, that if you put a script in a button and then move that button onto a different card or into a different stack, the button will still work because the script travels with the button. Also, there was a delegation model, in that I could put this script in a button, and then if I click on the button, then the script will run. Or I could put it in the card that the button is on, and then if the button doesn't handle it, then it delegates to the card. Again, that might seem very familiar to some of you, and we'll see more of that in future evenings. So HyperCard had stacks of cards containing buttons, images, text fields. It didn't anticipate color. It was a strictly one pixel black and white system. So it didn't always look very good. And that may have been because Bill Atkinson was colorblind and just didn't see the need for it. It had things you could click on and and then go to something else, go to a different stack or a different card. But it didn't allow you to put the links inside of the text fields. That was an obvious thing, but they just never figured out how to express that. And probably the biggest limitation was it didn't anticipate networking. So everything was expected to be distributed on floppy disk. Also, it had a terrible security model, because if you loaded someone's stack onto your machine, and if it came from an evil person, they own your machine now. So it didn't protect you from that kind of stuff. So almost overnight, HyperCard just sort of collapsed. It had been the biggest thing anyone had ever seen, and then it virtually disappeared. So winding back a little bit more, going back to Engelbart's system. Engelbart's system at SRI was not just a demo, it actually worked. It was a real system. SRI sold his system to a timesharing company called Timeshare, and then Timeshare was sold to McDonnell Douglas. Then McDonnell Douglas buried it. So unfortunately, that stuff didn't go forward. It died inside of that corporation. But Engelbart was a big influence on Ted Nelson. So Ted Nelson came up with an extremely ambitious hypertext system called Xanadu. In fact, Nelson invented the term hypertext. And his system had bidirectional links in it, and transclusions and inclusions, and a payment system, and all kinds of stuff that he considered to be necessary. And had a brilliant team of engineers building this stuff, but they never finished it. Xanadu had a small influence on HyperCard. Basically, that influence was the name. The hyper in HyperCard was lifted from the hyper in hypertext, but that was about the only similarity. Tim Berners-Lee's World Wide Web was also directly influenced by Xanadu, except he really didn't know very much about Xanadu, and he knew nothing about Engelbart. But as a result, it was really simple because he had never thought of all the really complicated things he can do. And because it was really simple, he was able to implement it. And it turns out getting the thing done counts more than just about anything else. So the World Wide Web itself was influential. And so after Sir Tim published his specs, a lot of people started imitating it. The most famous of those was the Mosaic project at the University of Illinois at Urbana-Champaign. They developed the Mosaic browser. At that time, there was a handful of protocols that were all contending to be the popular front end of the web. And this team couldn't decide which of those was going to win, so they made a program that could implement all of them. It could do Gopher and Wace and everything. And they called it Mosaic because it was made up of all of those different pieces. It turned out the web component was the one that people liked because they added an image tag to it, so that even though it wasn't what everybody wanted, it could be made to look exactly like what everybody wanted, and that was enough to send it to the moon. So Mosaic and the web became extremely popular after that. And then that team split into two separate startups, Netscape and Spyglass. Netscape announced that they were going to destroy Microsoft, so Microsoft bought Spyglass and turned it into Internet Explorer. Netscape had an idea to take the ideas in HyperCard, particularly that easy-to-use programming model that was event-driven based on buttons and fields, and put that into the browser. And they hired this guy to do it. That's Brendan Eich, brilliant guy. They hired him out of Silicon Graphics. They asked him what he wanted to do, and he said he wanted to write a scheme interpreter because he'd read this scheme report and thought it was really cool. So they said, great. They hired him and then said, but you can't do scheme. That's just too weird looking. People won't like that. Make it look more like Java. So he designed a language that looked more like Java. Basically, he took these components. He took the syntax of Java. He took the function model of Scheme, which was brilliant, one of the best ideas in the history of programming languages. And he took the prototypal objects from Self. And he put them together in a really interesting way, really fast. He completed the whole thing in a couple of weeks. It's a shame that he wasn't given the freedom that Xerox had to spend a decade to get this right. Instead of 10 years, it was more like 10 days, and that was it. And I challenge any language designer to come up with a brand new design from scratch in 10 days and then release it to the world and call it done and see what happens with that. One of the consequences of it was that there are parts of it that are just awful. If they'd had more time, they probably would have recognized that and fixed it, but they didn't. Netscape was not a company that had time to get it right, which is why there's no longer a Netscape. But despite that, there is absolutely deep, profound brilliance in this language. And this language is succeeding in places where many other languages have failed because of that brilliance. It's not accidental that JavaScript has become the most popular programming language in the world. Many people may not remember that the language of the browser was supposed to be Java. Java applets in 1995 were the hottest thing anyone had ever seen, and they were going to rule the world. They were hotter than HyperCard. It was going to be big. And the Java community doesn't remember this. Java failed on its face, hard, total, complete failure. They managed to find a niche on the server side, and so there's good in Java, and so it survives, good for them. But for the thing that Java was intended to do, the thing they told Java, this is what it's all, what they told the world, this is what it's all about, Java totally failed. In that same venue, JavaScript is succeeding brilliantly. So the argument that, well, it's just luck, because it's in the browser, that's why it's doing so well. that completely ignores history, because Java was in there first and got every break. Just being in the browser was not enough to assure success. And we'll be talking more about what the language got right and wrong in future episodes. So in 1969, Gene Samet wrote a brilliant book called Programming Languages, History and Fundamentals, which was basically a survey of all of the work on automatic programming that had happened in the 50s and 60s. And she counted over 100 languages, which she describes in her book, because that was a time of amazing innovation. And I'm very happy that we are, again, in another of those periods of innovation. We've got a lot of interesting languages now, including some pretty wild designs like Haskell, Erlang, Scala, which are all getting attention. And there are lots of other languages which are also getting attention. One thing that's different now than in the 50s and 60s is there are a lot of computers out there, and there are a lot of people writing programs now. So it's possible to get a community of people, even if you have a minor language, enough to do useful things, to do a lot of group work, and you've got a group large enough to justify writing books, which was something that we didn't have back in the 50s and 60s. So I think this is a great time to be a programmer. We have lots of choices, and we need to be smart about making those choices and be open to accepting the new ideas, because there are a lot of new ideas out there that we shouldn't be rejecting just because they're unfamiliar and we don't see the need for them. There are actually a lot of good ideas in all of these languages, not least of which is JavaScript, which will be the subject going forward. So there's much, much more of this history. The history of computers and of software and programming languages is incredibly rich. I was only able to scratch the surface of it in these 2 hours, but I highly recommend that you take a deeper look at it. Next time we'll come back here and do chapter 2, and we'll look at JavaScript, I promise. Okay. Thank you and good night.